This video is Banked Turns 2. A battery-powered toy plane of mass m attached to a string of length L circles horizontally at a constant speed v and makes a constant angle theta with the vertical. Derive an expression for the speed v. When in doubt, draw a free body diagram and use Newton's second law. Here we go. Let's draw the mass at that instant. And what are the forces that are acting? We've got mg acting downward. The tension is along the line of the rope. So the tension is going to go kind of like that. And if that's the angle theta given in the picture there, then isn't it true that this angle is theta as well? So let's use Newton's second law. Now, the key to this, again, is that the acceleration is entirely to the left. Let me draw a little arrow there. See that? The acceleration of this is towards the center of the circle. Look at the picture on the right. You see, that's a circle. And this toy plane is going around and around a circle. And so at that instant, it's accelerating directly to the left, as I've shown here on the left side of the video. And our coordinate axes, one of them has to be pointing in that direction. So I'm going to make my x-axis point in that direction, and then I can make my y-axis point up there. The fact that that's not a right-handed coordinate system doesn't matter. I'm just using that for reference. The reason I bring this up is because many times in my first year physics class that I teach, we have to break the weight into components a lot because we're talking about inclined planes. But in a case like this, when we know that the acceleration is in a particular direction, we have to have one of those coordinate axes in that direction. So for this problem, mg is not going to be resolved into components. It's the tension that has to get resolved into an x component and a y component. All right, so let's see if we can do this. Let's sum the forces in the y direction. Tension times the cosine of theta upward minus mg, and that should equal the mass of the object times the acceleration in the y direction. The acceleration in the y direction, this toy plane, it's not going higher up or lower down, it's staying in the same vertical plane. So that means that the tension is equal to, can we solve this for tension? Mg divided by cosine theta. All right, so far so good. Let's write a Newton's second law equation in the x direction. Let's sum the forces in the x direction. Well, the only force that's acting in the x direction, see what we've drawn over here on the left, is t sine theta. That's the only one that's acting in the x direction. So that is the net force in the x direction, and that should equal the mass of the object times the acceleration in the x direction. Now, the acceleration in the x direction is generically, it is, isn't this right? I'll put these in quotes. V squared over r. That's what it is. Well, the v squared is fine. Nothing wrong with the v squared. But what's r here? Watch my pen here. That's r right there. That's the radius of curvature. And what's that numerically equal to? Isn't it L sine theta? So this denominator here turns into L sine theta. Hope that made sense. All right, well, let's see what we have then. This gives us, I'm just going to spend an extra line here, making sure that we don't make any mistakes. T sine theta equals mv squared over L sine theta. Now, we're looking for v. We know m, we know L, we know theta, but we don't know the tension, but we solved for that just a second ago. So that tension turns into mg over cosine theta. So let's see if we can simplify this without making any mistakes. It looks to me like the m's cancel. If I put the L on that side and the sine theta on that side, we're going to end up with v is equal to sine theta squared. There are a couple ways you could do that. Then you have to take the square root. So you might want to check this and make sure I don't make any mistakes here. I'm thinking that we're going to get that, and then g times L divided by cosine theta. All of that is still under the radical.